Okay, and next, let me go through a list of actually 3 tests um, under general framework of non-hypothesis significance testing. So first is called the Wald test. First is called the Wald test. So note that maximum likelihood estimation theory shows that the maximum likelihood estimators, okay, from this case, in this case, from binary regression model, and later on from all the categorical and limited response variable models covered in this course, follow an asymptotic normal distribution. So asymptotic normal distribution and parameters and the variance covariance matrix. Okay, so this is an example, right? The variance covariance matrix. So this is variance for beta 0 hat, beta 1 hat, beta 2 hat, and you know, that's how the matrix looks like. And here, just a quick question for you to think about. Here, I'm not going to give you an answer. Okay, so what does sigma beta 1 hat, beta 2 hat tell you? Okay, so what does a Wald test do, and how is the calculation carried out? But basically, what the Wald test does is it's gonna, gauge the distance, okay, gauge the distance, let's say between, beta 0, beta ML hat and beta equal to 0 in this case. Okay, if the non-value specified is 0, sometimes it's not specified with 0, but in most cases it's specified as 0. So basically, what it does is it's look at the distance between these 2 values, right? This is ML estimator, right? And then it's going to look at the curvature of this log likelihood function. So this is a beta function. This is a beta function, right? This is, beta maximum likelihood estimator, and this is 0. So we're going to look at the distance here, then we're going to normalize by the curvature of this function from here to here. Okay? The second derivative. And see if this distance is big enough. So the distance here is going to be normalized by some function of the second derivative. So here actually is the second, is a function of second derivative, right? It's called Hessian matrix. And so there's a -1. So the variance of ML estimator is the inverse of the negative of the expected Hessian matrix. So basically, look at is something related to the second derivative of the log likelihood with respect to beta ML. In this case, actually, is this value, right? Is this value. And if this is big, second derivative is big, okay? That means it is very steep. The curve is very steep. So it's going to be something like that, okay? The second curve is very steep. Actually, the second derivative is evaluated here. Okay, the second derivative is evaluated here, okay? At the value of ML estimator. So if the second derivative is big, is large, then that means it is very steep, right? The curve is very steep, okay? And if this is very large, then the inverse of that value is going to be very small, okay? And if we use, the distance to be normalized by, that very small variance here, we're going to get a huge, huge test statistic. And then we can reject them now. All right? And that's kind of a general idea. So basically it says, well, the larger, this implies that the larger the curvature, the smaller the variance, spread, or standard error of ML estimates. And more likely, we're going to get a large test statistic. Actually, it's chi-square, and very likely, we're going to reject the null. Okay, so let me continue discussion about Wald tests. So let's say we have unconstrained estimator beta hat that maximizes the log likelihood. Okay, so like that. It's unconstrained model. That is, we don't impose any constraints. For example, this sum beta equal to 0, right? And here is the null hypothesis. So with beta set to be 0 in the null, okay, that constraint, then basically that says the constraint estimate is beta hat equal to 0, right? Assuming the null is true. If the unconstrained value estimate turns out to be 0, then the log likelihood of constrained is equal to the log likelihood of unconstrained. Okay? That is, if we run unconstrained model, okay, it turns out that beta equal to 0 after some check, then these two are going to be equal in theory, constrained and unconstrained. With the constraint that the beta equal to 0. Otherwise, the log likelihood of constraint is always going to be smaller than the log likelihood of unconstrained, because the unconstrained model is more complicated. Okay, and a complicated model should have a high probability or likelihood of observing the data. And because log function is monotonic increasing function, a greater likelihood or probability leads to a greater log likelihood. Excuse me. And then we estimate the model without constraints and assess the constraint by considering the distance. So we're going to estimate the full model, the unconstrained model. Okay, we're going to gauge the distance and then the curvature of log likelihood, okay, indicated by the second derivative, actually, the Hessian matrix. Okay, as discussed in the previous slide, and also this slide. So this is the second derivative, curvature. The greater the value is, the smaller the variance. So that's given fact, okay, for ML estimators, how to calculate its variance covariance matrix. It's alpha ticket inverse, right? So if this is large, if the Hessian is large, Hessian matrix is Hessian, Hessian matrix, okay, basically the second derivative, okay, of log likelihood with respect to estimator here. The variance going to become small, and the variance becomes small, then the tested statistic going to be large. Okay, so here we have dashed lines, right? This is dashed line. For the dashed line, log likelihood is nearly flat. So second derivative is relatively small, right? Smaller curvature. When the second derivative is small, okay, we're going to have large variance. And the distance is minor relative to the sample variation, right? So let's say the same distance here. Log likelihood is, curve is this one. Greater variance. So that distance is small. So it's always relative to the log likelihood curve, right? For the solid line, log likelihood has a larger second derivative than a more rapid change in likelihood function, right? So this changes much faster. With a larger second derivative, the same distance here, okay, might be significant, right? Might be significant. Okay, so how would increasing the sample size? Next, I want to talk about is how would increasing the sample size affect the curvature of the log likelihood function? Well, when the noun is true, as n increases, the sampling distributions of the Wald test converges to chi-square distribution with degree of freedom equal to the number of constraints. Excuse me, be tested. Okay, so first is a question for you to think about, and second is a statement here. So when the noun hypothesis is true, as n increases, the sampling distributions of Wald test converges to the chi-square distribution with degrees of freedom equal to the number of constraints being tested.